Okay, so we're going to study our vibration system. It's a linear system and discrete, and which is the finite number of the mass, and then deterministic. And actually, the function is given the time function. Can be constant, can be periodic, like harmonic motions, and then can be combination of the harmonic motion, and or it can be arbitrary, like the step input. Okay, if you have taken control, then you should know the step input, like this one. Okay. So nowadays, let's go to the section 6 and the procedures. And here I'm going to describe is a little bit more general terms. So the first step is called the mathematical modeling. So that means apply Newton's law as a first tool. And even for the multiple degree freedom systems, I'm going to teach you, say, using Lagrange equations. Okay, and that kind of energy based. You need to formulate kinetic energy and potential energy, and then do some kind of special term in chapter 5, or we're going to have that one. Okay, whatever the tools you learned from dynamics, and they're going to use here. Okay, and once you have that kind of formulation, basically you're going to have the differential equations, linear differential equations, something like this. A x double dot plus b x dot plus cx. Okay, and for free vibrations, then will be like this. And ABC are the functions of the mass, springs, and damping. Okay, so basically ABC are certain constant. Then for free vibrations, you're going to have this term is 0. And then hopefully you still remember how to solve for xt. Okay, and you know for differential equations, we are given the initial conditions. So say x0 equal to, say, certain numbers, and initial velocity so equal to v0. So that is kind of concept here. We impose initial conditions. So with those things, I can tell you that more than 90% of your time in ME408 is to deal with such solutions mathematically. So basically from here, I would say the majority of the content you're supposed to learn, you have learned from the DFEQ already. Right. Okay, so my job is not the solution, although I will give you the just-in-time review, how to do it quickly, correctly. My job will be, most of the time, will be here, 3 and 4. So once you have the solutions, then how to give the kind of the good interpretation to the mechanical systems. How to use the result and to explain some situations. So here we're going to have the solution and we're going to interpret the result. And that is the portions after you're spending, most of the time in the solution process. And that is a key step. You have to spend a little bit more, just be patient a little bit more, and then that's going to learn from here. Okay? For the mathematical modeling, and basically here we're using the lumps. So basically we try to discretize the systems. And from the beginning, in the first 2 months until end of October, our system will be most likely like this. Okay, so basically that is a little bit easier than discretizing the system. How to discretize from the continuum to here, that won't be touched here. That could be covered in the advanced vibrations. Okay. Derive the equations. We're going to use Newton's law, second Newton's law. And the majority of this one was really based upon what you have learned from dynamics. And so probably you can dig out. And most of the time we kind of using a lot is the translations. So which means translation, that means x double dot equal to external force. Okay, for example, something like this. Okay, and also we're going to deal with rotational degree of freedoms. So sometimes the total the torque, okay, will be equal to I. Whatever I would say depends on the symbols and theta double dot, right? And this I will depends on if you have the memories. Rotation is a little bit tricky. That really depends on which locations you talk about. At the different location or rotating in respect to the different, I would say, center of the rotation, that has a different number for this one. So this trend do need a little bit review from you. That won't much, okay? So kind of grab it and just for your attention here. So free body diagram we're going to use from day 1, day 2, and then I'm going to introduce the energy method. I don't know how the ES210 has stretched out to the energy method, but I will provide a little bit more review on this one. And again, all of our equations are the ordinary differential equations. Sometimes I use a term called ODE. Okay, that is in terms of mass, that is the system we're going to deal with. And again, initial conditions, and that is always not to forget, always try to remember. Whenever we are dealing with a dynamic system, we always constrain with the initial conditions. Different initial conditions will give us the different result. Although the template of the XT is the same, but in terms of numbers, that really up to the initial conditions. Okay. Now the solving the Gaussian equations, and again, this one I will give you the just-in-time review. And about the ODE, okay, don't worry, but the details I will leave to you. So everything come together to the ME408. I hope this will be the last class for most of you kind of the math rigor or math oriented. Hopefully this will be the last one, and I guarantee I will help you through this. Okay, and what kind of preparations, and we talk about here, I'm not scaring and not kind of scaring you, but kind of asking you to kind of reflect at this moment. So you need to know, at least expose yourself to the solution to ODE. So using the Math 201 or 301, combining with the Math the DTEQ, we're going to use the Fourier series expansions, and that kind of things a little bit going to decompose the functions, any type of the functions. So you can use this one. And in terms of the solution process, and sometimes the plot transform will be, sorry, my mistake, not transformation, only transform. Okay, the plot transform will be easier. And this one been talking, I don't know whether in Math 201 or ME409. If you have taken the ME409, that will be your advantage. But again, I will review the Laplace transform in this class as well. Okay. And convolutional integral, and that is a very unique approach. Unless you really study the dynamics, otherwise this convolutional integral won't appear in that kind of topic. Okay, so this is a very particular mathematical tool. And again, I'm going to review this one as well. Linear algebra, basically majority is we're going to apply the eigenvalue problems. Again, I will give you a review. So those kind of solution process, we're going to mix them. Depends on the situations and depends on how you be familiar with the process. And either of the math tools will be okay for solving all kinds of the differential equations. I can guarantee, okay? But the matter is how much time you're going to spend, okay? The last one, the programming in particular for using MATLAB. And assuming you have that kind of foundation, so this one I won't provide too much review. I'm assuming everyone should have that kind of the preparations. Okay, if not, I can provide you some kind of the PDF handout about using MATLAB, and in class I'm going to quickly go over using MATLAB how to solve particular questions, and I will have some, but I won't teach that one. Okay, so that is about this. Any questions?